Today's lab, we're going to synthesize aspirin, acetyl salicylic acid, and then take a look at a couple properties of it in terms of the reaction. Did it go to completion? And to do that, we'll use an iron 3 chloride solution, and then we'll also heat some of the acetyl salicylic acid, i.e. aspirin, that we prepared. Heat that up and see if we notice any distinct odor or smell. So first, just want to talk a little bit about what you have seen previous to this lab is how to make an ester. And I'm going to kind of go backward in this reaction just to kind of reemphasize that part. What you have been taught earlier is that if you have an alcohol, now this is an alcohol, even though the OH group is attached to the benzene ring, it does participate in many of the same reactions that non-aromatic alcohols do. So if you have an alcohol and you have a carboxylic acid, we saw in a previous lab that you can make an ester by splitting out water. You take the OH off the carboxyl group and the H off the OH group, and you would end up forming an ester plus water, and I'm just kind of showing that underneath here. What we also said about this particular reaction, if we're going in this direction, that if you do that, the yield of that particular reaction is not great to synthesize the ester because of low reactivity of the carboxyl group compared to the alcohol. So what we're going to do today, we're going to take the alcohol, but instead of mixing it or reacting it with the carboxylic acid, we're going to react it with a derivative of a carboxylic acid, and this is referred to as an anhydride. When you have anhydrides, you always recognize those because the oxygen is sandwiched between two carbonyl groups. And you can have mixed anhydrides, or you can have what we call simple anhydrides. This is an example of a simple anhydride because if I kind of cover that oxygen up and look to the left and look to the right, what I see are equivalent groups present. So in terms of this, and again, this is not a true mechanism. This is what I call lasso chemistry. And I want to say something about the anhydride. The specific one we're using today is acetic anhydride. These acetic anhydrides are much more reactive than the carboxylic acid they were derived from. And because of that, you do have to go to a little bit of trouble making sure that they don't react before you want them to. You typically want to make sure that you expose them to as little air as possible before you're using them, because water can come in and actually hydrolyze this back to a carboxylic acid. They are very reactive. They are strong lacrimators, so you want to make sure that you use this compound under the fume hood that can cause your eyes to run and so on and so forth. So what we're going to do here is we're going to take off the hydrogen of your phenolic group. And it doesn't matter which side of this oxygen I break that bond, but I'm just kind of showing it on this side. You get the same product no matter what. And notice what happens is that the hydrogen will combine with this oxygen to form acetic acid, and then this oxygen will hook up to the carbonyl group of this side of the molecule. So notice nothing changed with the carboxyl group originally attached to salicylic acid, which is what we're starting with. But notice now the oxygen isn't bonded to the hydrogen, it's bonded to this group here. We call this an acetyl group. Oxygen's bonded to the carbonyl carbon, then the CH3. And then remember, this picked up a hydrogen from salicylic acid to form acetic acid. Now when we do this, we're going to kind of go through and rinse our product so that we can remove all of this. This is soluble in water, and acetic acid is responsible for the smell of vinegar. So we're going to wash this as we collect it, so there should not be any of this left in our product that we've prepared. And just a little bit in terms of why they, and this is what we call aspirin, but why they went through this process. When people first took salicylic acid, they noticed they had a lot more acid upset or stomach upset from increased acidity. The thing about this is what they did, phenolic groups, they're not strong acids, but they do have acidic properties. This can also ionize and then cause irritation of the stomach lining. So what they've done is to esterify this And this molecule here, aspirin, which is acetylated, they esterified that oxygen, is that it really doesn't interact, break down much in the stomach. It's really not changed until it reaches the intestine where there's an alkaline environment. So the main reason they esterified this OH group is for that acid upset. Now, one of the things we're going to do is at the end of the reaction, once we collected our product, we're going to test it for the iron 3 chloride test. And if you remember from a previous experiment, what the FeCl3 test picks up are phenolic groups. So we're going to test what we made, and we're also going to compare it to the test of what we started with. Remember, phenolic groups in the presence of iron 3 chloride can change the color of that yellow solution of the iron 3 chloride. What color it changes, it could be blue, purple, red, depends on what other groups you have on that benzene ring. So if we test our product and it gives us a color change, then what that tells us is that this reaction didn't go to completion. We still have some unreacted salicylic acid present. If this is negative, meaning no change, then we feel pretty comfortable that what we prepared was the acetyl salicylic acid. One other thing we're going to do is to take our product, a little bit of our product, and then we're going to heat it. And after we heat it for a few minutes, I'm going to take a whiff, if you will, of the sample, notice the odor to see if there's an odor change. And what happens in the presence of heat is that the esterified group, this acetyl group, will cleave in the presence of heat. You also need moisture, but remember when we collect this, it's still going to be probably a little bit damp because we're collecting it from an aqueous environment. So if you have moisture present, then you can certainly cleave that esterified group, the ester link, and get back your starting material, which is salicylic acid, and then vinegar. And if I can test the presence of that, then I'll pretty much know, again, that we have made our product that we said we did. The other thing, just to kind of point out to you, sometimes I hear people ask, well, why do they put cotton in some things and not in others? And a lot of times they do that to keep the tablets from bumping around and breaking in that specified container. It's probably not a good idea to pack cotton in with aspirin, because what can happen is that each time you open that bottle, some of that cotton can absorb moisture from the atmosphere. Now you've got moisture present, and over a period of time, you can certainly have that hydrolyzed product form. Doesn't necessarily mean that it's bad, so to speak. It can certainly cause more upset than the esterified product. But if you ever smell vinegar in your aspirin bottle, then that means some of that has already hydrolyzed.